This is Unit 5, Lesson 6, Part 1, Optimization. Optimization is one of the biggest reasons that calculus is studied and used. We look for things like the least amount of time, greatest profit, shortest distance, maximum volume, minimize waste. We want to optimize a situation to save money or to make money or to streamline a process. So you want to make sure that in these problems that you pick apart the information, that you'll be given several different pieces of information. You want to make sure that you identify what you're to optimize, so what is to be maximized, what is to be minimized, and separate that from a constraint, which is usually what causes these problems to happen in the first place. You want to put so much volume of peaches in a can, but you want to keep the cost of manufacturing the can down. So you want to use the least amount of aluminum, things of that sort. So let's start with the most basic example and work our way through these. Okay, so number one, we are to find two positive numbers such that the sum of the first and twice the second is 64, and whose product is the maximum. So what I want to point out here is that we have two different pieces of information. The first one is this sum. The sum right here, that is our constraint. That's our constraint. But we want the product to be a maximum. That is what we're optimizing. Okay, so we have to assign variables. I'm just going to keep this simple. X is the first number. Y is the second number. And I'm going to call the constraint equation C is equal to the first number plus twice the second number. And that, excuse me, has to equal 64. Okay, our optimization is then going to be, I'm going to call that O, is going to be the area or the product, XY. So what I need to do is eliminate the variables. So I want to create an equation that is just in X, or you could do it just in Y. So going back to the first equation, I'm going to subtract X. So I have 2Y equals 64 minus X, then divide by 2. So I get Y equals 64 minus X over 2. So I'm going to substitute that into my optimization equation. And now, how these differ from what we've done in the past is, I'm going to simplify this equation, is we are going to take the first derivative, find the critical numbers, because those are where the mins and maxes are. So we can be exact about what exactly the minimum maximum number are without any gray area. So taking the derivative, then of course I'm going to set it equal to 0. And I get X is 32. Now, while you only have one number, you still should show that you're checking the fact that this is indeed a maximum. So you should do the first derivative test. So I'll try 30 and 40 to keep things simple. And so before 32, if I substitute that in my derivative, I get a positive number. And if I substitute 40, I'm going to get a negative number. So what I can see here is that I indeed have a maximum. So I can clearly state my two numbers. So my two numbers are X equals 32 and Y is going to equal 64 minus 32 over 2, which is 16. And so I can say that the numbers are, you want to make sure you write a statement. The numbers are 32 and 16. Now we're going to see in future examples, ones that are more detailed, that you're going to have to justify your answer, not just show your sign chart, as we talked about earlier in this unit. Okay, example 2. A rancher plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? Okay, so here is, let me do it in green, actually blue. Here's our river. Here is our river. And then we are going to put a pasture fence around it, something like this. And I will call these two sides Y. Here is my river. This side is X. Now what I do know is that the area is going to be 180,000 square meters. Okay, so what I want to optimize is the least amount of fencing. That's my perimeter. So my constraint is going to be the area. And we want to minimize the perimeter. So those are the two equations we're going to work with. And remember, the one we want to take the derivative of is the one we want to minimize. So we know that area is going to equal x times y, and we know that equals 180,000. And I'm going to solve this for y, so I get y equals 180,000 over x. So then, here is my perimeter equation. So P of x is going to equal, we only have 1x plus 2y because we have no fencing along the river. So P of x is going to equal x plus 2 times 180,000 over x. So we get that P of x equals x plus 360,000 over x. So now we're going to take the derivative, and we get 1 minus 360,000 over x squared. We're going to set that equal to 0. Okay, so taking the 1 over, multiplying by the x squared, I get this. X squared is going to equal 360,000. Using the square root of that, I'm only going to keep the positive value because I can't have negative length. And now I'm going to do my sign chart just to double check, because again, we only have one answer here. So 600 is my x. So I know I have to be above 0. So here's f prime, here's f. So I've tried 100 and 1,000 to make the calculations easy in the derivative, since I have this big number here and I'm squaring it. So putting 100 in, what I find is I get a negative number here. And so the function is decreasing. Make sure I get rid of that little f there. That shouldn't be f prime. It should just be f. And then at 1,000, when I substitute 1,000 in my derivative, I am going to get a positive number, so I am increasing. Okay, so what I find here is I have a minimum. So now I can answer the problem. I can substitute for y here, and so y is going to equal 180,000 divided by 600. So I get that y is 300. So I can say that x equals 600 meters, y equals 300 meters. And I know this because I can say that f prime, I should say p prime of 600 equals 0, and p prime changes signs from negative to positive. That's your justification. And that's why when I told you before that the readers don't just want to see the sign chart, you have to describe exactly why you know that that is a minimum. Okay, we'll do one more for this video. Number 3. Okay, so we have an open box that's being constructed from a piece of sheet metal, 18 by 30 inches, and we're going to cut out the corners of equal size and bend up the sides to make a box with an open top. What size square should be cut to make the box of maximum volume, and what is that volume? Okay, so we did problems like this in pre-calculus. We want to see that this little corner, it's hard to draw that really small with this stylus. Those are x by x. And if I make the box, what I have here is I have this little, there's my little x side. This side is longer. Okay, so there's my box. So the dimensions of my box, the front of it is going to be 18 minus 2x. And that measurement, of course, is x. And the longer side is 30 minus 2x. So what I'm going to do is set up my volume equation. So volume is going to equal x times 18 minus 2x times 30 minus 2x. So multiplying that all out, I get that my volume is 4x to the third minus 96x squared plus 540x. I did that when I started doing the problem because I realized I'd rather just do the power rule than do the product rule. So from here, we're going to take the derivative, and the reason we don't have a second equation, because our constraint is the fact that the x has to be somewhere greater than 0 but less than 9. Since if it was more than 9, this whole side across the bottom, you cut it off, and you're just making your box smaller. So we have 12x squared minus 192x plus 540. Now we're going to set that equal to 0. So I factored out the 12, and I had x squared minus 16x plus 45 equals 0. And of course that does not factor, but you can solve it by completing the square or using the quadratic formula. And I did this, and I got 16 plus or minus the square root of 76 over 2. And that simplifies to x equals 16 plus or minus 2 times the square root of 19 over 2. So I get 8 plus or minus the square root of 19. Now I have to use the one with the minus, so my only answer is x equals 8 minus the square root of 19. Otherwise, I would be past my constraint. Okay, so what do I do with that now? I am going to do my sign chart. So I have v prime and v, and I know can't pass 9 and 0 over here, so here's 8 minus the square root of 19. So what I did is I used 6 on this side and 8 on the other because I'm going to be less than 8. And I used a calculator at this point, and I substituted 6 in and got a positive number, so I'm increasing. And when I substituted 8 in, I got a negative number, so I have a max here. So I can figure out the volume. So next I substituted v of 8 minus the square root of 19 in the calculator, and I got 886.552 cubic inches. So my answer is going to be the volume of 886.552 cubic inches will be the maximum since, and again I'm going to write v prime of x equals 0 and v prime changes signs. From positive to negative. And then So I have my two answers. And I also want to make sure that I include that x equals 8 minus the square root of 19, because it asks for the x too. Okay, so this is the end of this video, and I'll do some more practice problems in the next video.